To calculate the pH from a hydrogen ion concentration, we need to remember that pH equals the negative log, that's the log log, the base 10 log, of the concentration of the hydrogen ion in molarity. So what we're given to here in number 1, when you have these square brackets, that is to indicate the concentration of, and it's going to indicate concentration in molarity. So all we need to do is plug this value into the pH equation, 1.03 times 10 to the negative 3, and we get that the pH is equal to 3.0. Now that is an acidic solution. For number 2, we have the hydrogen ion concentration of 2.4 times 10 to the negative 5, so we put that into our calculator, and you may have to work with your calculator to see, do you put in the number, the value, and then punch log, or do you put in the number? It is recommended that you use scientific notation, so that involves using the EE or maybe EXP on your calculator. I don't know, but if you send me a picture of your calculator, I can help you with the keystrokes. So the pH of this is going to be 4.6. Number 3, we're going to put this value into our calculator with log. So pH is going to be equal to the negative log of 5.11 times 10 to the negative 13. So when I put that into the calculator, I get 12.3. Now I forgot to tag this. This one is an acid solution. So this number 3 solution, being a pH of 12.3, means this is a base. So what we're doing is we are defining that a pH, when the pH is less than 7, we'll call that an acid. When the pH is equal to 7, we will call that neutral. And when the pH is greater than 7, we call that a base. For number 4, we're given the hydroxide ion concentration. Now, hydroxide is different than hydronium, and it is different than hydrogen. Hydroxide is negatively charged. There are 2 different ways that we can calculate the pH from the hydroxide ion concentration, and I'm going to show you both. The first way I'm going to show you is to calculate the concentration of the hydrogen ion from hydroxide and Kw. So Kw we know is 1.0 times 10 to the negative 14. And we're looking for hydrogen ion. We have hydroxide, 7.352 times 10 to the negative 2. So I divide my 1.0 times 10 to the negative 14 by 7.352 times 10 to the negative 2, and I get a hydrogen ion concentration of 1.36, let's see, we have 4 sig figs, so 1.361 times 10 to the negative 13. I'm leaving this value in my calculator in order to avoid rounding error, and I'm just going to punch the log button from there. And when I do that, I get a pH, which we have found by taking the negative log of the concentration of the hydrogen ion. I get that my pH is 12.87. So now let's go the other way. So this is a base solution. Let's show you the arguably much faster way. So I was given the pOH with number 4. Now I'm going to take what's called the pOH. So I'm going to take the negative log of the concentration of the hydroxide ion. So the pOH is then going to be the log value of 7.352 times 10 to the negative 2. The pOH is 1.1, 34. But I'm leaving the value in my calculator. I actually get 1.13359, etc. So now I'm going to use the identity that the pH plus the pOH is going to be equal to 14. That means I can solve for the pH, and it happens to be 12.87. So you see, either way, you should end up with the same value. And again, this is a base solution because the pH is greater than 7. Number 5, we have a hydrogen ion concentration. So that's the easy way for us to do this. The log of this value, 3.5 times 10 to the negative 6. Punch that in my calculator. And I get the pH is 5.4, well, we'll call that 5.5. Number 6, again, the hydrogen ion concentration. The pH is equal to the negative log log of 1.0 times 10 to the negative 7. So the pH is 7.0. For the next one, number 7, we are given a hydroxide, so the negatively charged atom or ion, hydroxide concentration. I'm going to use the pOH method. So the pOH of this is the negative log of the concentration of the pOH, 6.85 times 10 to the negative 10. And I get a pH value of 9.16. But now the question isn't what is the pOH, it is the pH. Oh, and I forgot to say this one is neutral because the pH is exactly 7. So again, back to number 7. We have the we have the pOH, now we need the pH, which is going to be 14 minus the pOH, which is 4.84 for this solution. And this is an acid because the pH is less than 7. Here we have a pOH, and here I'm going to do it the other way, where I calculate the concentration of the hydrogen ion, and I'm going to use the Kw of 1.0 or times 10 to the negative 14, and I'm going to divide that by the hydroxide ion concentration, 4.99 times 10 to the negative 8. So I get a hydrogen ion concentration of 2.00 times 10 to the negative 7, and that is a capital M molarity. And then I need to find the pH. So the pH is going to be the negative log log of the concentration of the hydrogen ion. So I get 6.70. Now this is ever so slightly acidic. And that's what we would call it. That's actually what we would call it in a laboratory. We would call this slightly acidic. And that's really what we say if we are within 1 pH unit. So 6 to 7 we call slightly acidic. 7 to 8 we would call slightly basic, although fundamentally a half a pH unit, we end up calling it just neutral. But for the class's sake, we would call this slightly acidic. By definition, it is less than 7. Number 9, hydrogen ion concentration of 3.389 times 10 to the negative 1. That's going to be awfully concentrated. So the pH is the negative log log of 3.389 times 10 to the negative 1, and I get a pH of 0.3389. Moving on to number 10, we're going to calculate the hydrogen ion concentration from each of these pHs. So 6.3, we would call this an acidic environment. I didn't say that this one was acidic, but it is, it's less than 7. 6.3, fundamentally, we call that acidic. Now, in order to get the hydrogen ion from the pH, we are still using this equation. But now we basically have to undo that log because now what we have is this value here. So we need to take what's called the anti-log. Now on your calculator, it's probably a second button or a shift button and then the LOG button. Now on my calculator, and I'll try to find a picture to insert into the video, I have this, and then above it, I have this kind of symbol. So I have a shift button, and this bit here is the color of my shift button. So I punch shift this button, and then I would type in negative 6.3. Because what that does is it takes 10 to that power, and that is equal to the concentration of the hydrogen ion. Now, it is possible to simply put 10 and then use your caret key. I'm looking for my caret key on my calculator right now. So some calculators will have this kind of a button. That's the caret key. It raises something to an exponent. Some calculators will have a button that is X and then like a box. Okay. It is possible to punch in 10, this button, and then change the sign 6.3 regardless, you should end up with the same answer. So you should end up with 5.01 times 10 to the negative 7, regardless of which way you do this. If you have questions about how to work your calculator, send me a picture of your calculator with a request to help you with which buttons to press to figure out the hydrogen ion concentration from pH. So for 8.17, fundamentally what we're doing is we're taking 10 to the negative 8.17, and that's going to be the concentration of our hydrogen ion. So 10 to the negative 8.17, I get 6.76 times 10 to the negative 9th, and that's a capital M molarity. This is a basic solution. The pH is greater than 7. Number 12, for 3.5, this is an acidic solution, and I'm going to take 10 to the negative 3.5, that's where this negative goes. You multiply both sides by negative 1, it goes over here. So 10 to the negative 3.5 is the concentration of my hydrogen ion, and that is equal to a value of 3.16 times 10 to the negative 4, capital M for molarity. 7.0, so 10 to the negative 7 is equal to the hydrogen ion concentration, and this is a neutral solution because the pH is equal to 7. Then we have 13.22. Now this is a basic solution. The pH is greater than 7, and so the hydrogen ion concentration being 10 to the negative 13.22, I get a value of 6.026 times 10 to the negative 14, capital M molarity.